Okay, so welcome everybody. Today we have a talk by Jialin Yu from Alibaba DAMO, and the topic is going to be towards explainable and reliable models for AI models for optimization, AI for optimization.
Thanks for the introduction and thanks for this opportunity to give a talk at University of Central Florida. And today I'm going to talk about my recent works on applying AI or machine learning methods on solving optimization problems. And
Probably you want to take the.
So yeah, I will stand here. Okay. So in a typical optimization work, so people usually first define a type of problem and then and manually develop a algorithm and then give some analysis on it and then pick some representative instances and do numerical validations on that. Well, if you want to apply machine learning methods to solve this kind of mathematical problems, so actually we want to learn an algorithm from data. A typical pipeline looks like first we collect enough data. It includes some problem instances and maybe with their solutions, and then we learn it from those data, and then we validate or test the learned algorithm on some new instances. So new instance here means that that testing instance shouldn't be included in the training set. We want the learned algorithm have some intelligence in it, but not just memorizing the training set. So later I will show what's the specific definition of like how to learn an algorithm from data. But before we dive into the technical details, let's first see a picture about the performance of learned algorithm. So in this picture, there are some curves, and the horizontal line measures the number of iterations, number of steps, and the vertical axis it measures an arrow. It's an MSE. It's an arrow. The lower the better. This curve, the blue curve, named the lista, is a learned algorithm, and the other ones, they are ISTA. They are manually designed algorithms with different parameters. And from this figure, we can clearly see the advantage of a learned algorithm. It performs pretty well on this problem. And also there are some other very successful optimization applications with this kind of methodology. So let's give a typical number. So if you like manually design an algorithm, it may take, for example, like 100 seconds to solve one instance. But if you want to use machine learning or use AI to solve a kind of algorithm, usually we have to pay more time for training. But after training, the learned algorithm is hopefully running much faster. So yeah, so if you have only one instance or you want to solve a single problem, so yes, I think in this case, yeah, so the manually designing an algorithm is a better choice. But if you have if you have enough data and you repeatedly solve a specific type of problems, in this case, I think the machine learning method is very worth to try. Yeah, and I also want to talk about some other impacts beyond just speeding up the algorithm. The first example is channel estimation. So in a communication system, like the signal receiver, like a phone, repeatedly estimating how the signal is affected by the environment, like the building, like the weather, something else. And this process is called channel estimation. And it can be formulated as an optimization problem. Yeah. So, and the problems usually formulated based on the latest information. So if you solve the problem with 100 seconds, it means that when you obtain the solution is based on the information like 100 seconds ago. It has a delay. But if you can solve the problem in just 1 second, the quality of the solution will be much better. Not just the speed up, not just the running time. The quality will be better because it depends on the latest information. Yeah, and the second example is a unique commitment in a grid system. So in a power grid system, like typically every 24 hours, people have to decide the operations of each unit, like open or close it, or set some parameters for it. This kind of problem is usually formulated as a mixed integer program. We want to minimize the running cost and satisfies some physical or energy constraints. So, but as we know, that the integer program is really hard, it's NP hard. So it's really challenging to solve it within 24 hours. It's almost impossible to get the optimal solution. So in this case, if we can get a faster algorithm, so hopefully we can get a better solution in 24 hours. So yeah, so it means that the cost of running the system will be reduced, and this is the potential impacts of like a learned algorithm. And so since 2018, the first year here, and until now, I continuously study this topic, and fortunately, have some papers on it. And today, I'm going to talk about some papers and show the major results. So currently, so in this topic, people are just regarding the AI models as a black box. Black box means it may work well, but we don't know why it works so well. It's not easy to understand that model, and it means that it's really hard to fully trust it when we want to make very important decisions, like it's have some social impact or very important to our careers. And also, there's no theoretical guarantee for the black box models, and it is quite possible that it has no guarantee and it works pretty well on the training side. But when we use it in the real system, when we test it, and it fails, and that's possible. So, therefore, we are targeting on the two fundamental aspects of this topic. The first one is explainability. So how to understand the learned models and why it works so well. And also the second one is reliability. It means how to control the models and make it more reliable. Yeah. So now I will start from a very fundamental problem in statistics. It is lasso, and so suppose now we have a signal x star. X star is a sparse and high dimensional vector, but we cannot directly access to x star. So we observe x star through a linear transform A, maybe some noise, and what we can observe is the observation B. So B is a lower dimensional but dense vector, and we want to recover x star from the observation B, and this can be done by this optimization problem. There's a lasso. The first term measures the difference between AX and B, and the second term is a regularization to limit the X to be sparse. And yeah, this is a very fundamental problem in statistics, and it has no closed form solution. People are typically solve it in an iterative way. And the E-star is a very basic iterative algorithm to solve lasso. So in this iteration, in this algorithm, so in the bracket, so we just do gradient descent. We just minus a gradient of the quadratic term, and the eta here, eta is the soft thresholding operator. It reduces the second term, reduces the one norm of x. So, and it alternatively handle the two terms in lasso. And so with a proper chosen alpha, this algorithm converges to the minimizer of this problem of lasso.
So the reason you're not solving, you're solving using iterative method because A is a very large matrix or response matrix, or what's the reason why can you solve?
Because the X is typically sparse and high dimensional. It's and the B is low dimensional, and A is like a downsampling operator. It's a underdetermined operator. So so if we directly solve AX minus B, it will be there will be multiple solutions. It's not well posed, and we need some regularizer to make it sparse, and this is what we want. So in this problem, people are just assuming the underlying signal to be sparse. So yeah, this is it.
But the reason you use iterative method is because of what? Like why do you use iterative when you just solve one shot?
So the lasso has no closed form solution. Yeah. So this is I think this is a very basic algorithm to like solve it. Yeah. And so there are some other papers, but not as like.
But I mean, this is not you can solve in one shot, right? You do pseudo inverse and so on. So what is the difference here?
So if we like just first solve the least square and then make some sparsity on the x, so it is an estimation of that problem, but not the optimal solution. And by iterative manner, we can like convert this to the optimal solution of that problem.
I guess question here, I understand that two questions. One is why you're assuming X is sparse. Why you add the L1 penalty there? That's some fundamental questions why people start in lasso in fact when this. Well, the second is that when you're solving this include algorithm, I think consider the role of lambda for statistically people are including some algorithm can find out store out the optimal lambda and use cross validation errors. By using this algorithm, you deal with the problems, find out the best lambda, the best sparse distribution in X.
Oh yeah. So for the first question, so why we assume it is sparse? So this problem is typically like in maybe like 10 or 20 years ago. So people are so in that case, people are usually assume that like an image or some other signals can be represented as a sparse representing a sparse linear representation of under some like basis or dictionaries. And so sparsity is not the only assumption. So there may be other assumptions like low rank or and also so it depends on our understanding of the specific applications. And so here because we are just targeting on solving optimization problems, and so we just pick this fundamental problem and as a start point, and I will show that some other in a more broad assumptions in this problem. And also for the second question, so why choose a fixed lambda here? So if we choose a fixed lambda here, there will be a bias here, and it is but I think this is so when we want to use a new technology to solve the problems, and this is a very fundamental problem. I think the first step is to start from the very basic settings, and yeah, and fully understand it, and then we push forward. I think this is the reason. And later I will show that actually in our algorithm, the lambda can be like adaptive.
Did that mean correctly, or use some A is sparse or X?
Oh, A is not sparse, X is sparse.
X is sparse. Is X a vector or matrix?
X here is a vector.
So I guess people from strategy department and from sales or other department looking at this problem from different angle. From stats point of view, I guess what they're looking for is why makes some of the sparse teaming problem, and from some other point of view, from optimization point of view, it's like given problem, how do we solve it? You know, the assumption was kind of given from the problem, and
So basically, what's the function of lambda?
Oh,
Like when you put a lambda, what's the difference between the solution here compared to the least square solution?
so the lambda here is to control to balance the two terms here, to balance whether you want to fix the like this term, and it means the least square. And
What's the effect of lambda
if the
on the estimates?
okay, if the lambda is larger, it means that you want the x to be more sparse, and in this case, the error may be larger, but the model is typically more robust. It means that if you have a larger noise, typically we choose a larger lambda.
because you want to be more sparse.
We don't so being more sparse is not the goal, but we want to balance the so if there's a lot of noise and we don't have any lambda, we set the lambda at 0, there will be a noise between ax minus b, and also it is not sparse. We can say that it is not accurate because we assume that the underlying xr to be sparse, and yeah, so in this case we have to set a larger lambda to
Just to minimize that left turn.
yeah.
To minimize the effect of that left turn.
Yeah. Okay, any questions?
Yeah, just continue.
Thank you. Yeah, and it's about 14 years ago. So Greg and LeCun reported a very interesting numerical results. They show that with machine learning techniques, we can so they can accelerate the E-star algorithm. And what they do is that they first rewrite the E-star formula. So they rewrite the A transpose term as a one matrix, and this term as another matrix, and rewrite everything here as a more general form. And then they unroll the iterative process and truncate it into capital K steps. In each step, they introduce a set of free parameters. So theta k, W1k, W2k, they are free parameters to tune. And yeah, so this formula is can be viewed as a new algorithm, but with a lot of parameters in it. And once the parameters are determined, we say we learn a new algorithm. So this is a definition of learning an algorithm. And this is an example. And what they do, they learn it from data. So they first, in their experiments, they assume that A is fixed, and in the later I will show that A can be any A, and yeah, and then they.
So basically, what it says is that instead of go back to the last page. So instead of learning one best lambda in this formula, where you're learning optimal lambda in every iteration, you're using different lambda in every iteration, which will increase the performance.
Yes, the theta k can.
So I guess compared to the traditional stats method, that finding the best lambda in the original formula, now you're finding a different lambda in every iteration. Not only one best lambda, the best lambda in every iteration.
Yeah. Okay, and what you do is their data collection is like first a fix, assuming a fixed A, and then generate a set of sparse vectors, X star. and then calculate calculate B accordingly, and then form the X and B as the training set. So since A is fixed and B can uniquely describe a problem instance now, and so B is a problem and XR is a solution. So yeah, so we just treat the XR and B pairs as the training set, and then they find those parameters by minimizing this function. It's called a loss function, and the loss function. So for each instance, we want the last iterate, the xk, the last iterate, to be as close to the ground truth as possible. And the performance is an average. E here means expectation. It's an average on the whole training set. Yeah, and we want to find the optimal parameters for the whole training set. Yeah, and this minimization problem is actually much more complicated than the problem before. But we don't have to solve this problem to the optimum. We just want to find a better parameter settings. Find parameter settings better than the vanilla ISTA.
So one quick question, but here you fixed the type of the solution that you want to obtain, meaning xk plus 1 has to be beta of w and so on.
Yeah.
So you're not discovering that solution itself.
Yes. So in the next part, I will show like how to learn an operator. That's yeah. So yeah. So and this kind of work can be so nowadays we can like easily implemented by some deep learning frameworks that we can just as a researcher, what we have to do is to first define the iterative formula and then define the data set, and that's enough. Yeah, so this is a training. So once it is trained, and yeah, we learn an algorithm, and we want the learned algorithm can be applied on some new coming instances, new coming Bs, and this is the this is our reproduction of their method, and we can clearly see that okay, the learning is much faster. Yeah.
The difference is the earlier case you don't need any training set. Here you need to have some training set extra.
Cleaning?
You need a training data extra in this case, right?
Oh, so in the testing set and training set, we assume that they follow the same distribution. Yeah, and yeah, we just randomly generate the sparse XR, and yeah, so they follow the same distribution, yeah, but independently generated in training and testing.
In GPT, you have to train it for how many months, right? I mean,
Right, but this one, for this one, you don't need any kind of external data. You are generating your own training. You assume that you know the A, right? So that's the work point, and you generate the multiplying power that noise, and that's your training data.
so I guess this is a synthetic framework. I mean, you could also collect the real data and then make it down to a specific real application.
Yeah, so that was I was going to ask. So what's a real problem where this occurs, and can you use a real data compared to synthetic data?
Oh yes, we can use the real data. Yeah, but I didn't show here, but I will show it in the next section, and it's a more flexible framework. Yeah, we have it. Yeah, yeah, and yeah, this is the quick review of the difference between Lisa and ISTA. Yeah, in ISTA there are only two parameters here, but in Lisa there are a lot of parameters here, and it depends on the size of the problem, and therefore it's really hard to manually tune those parameters. So this is the reason why we have to use deep learning softwares to obtain those parameters. Okay.
So the plot you were showing, the y-axis is the error, MSE is error between the ground truth solution.
Oh, sorry, I forgot to explain that. Oh, the NMSE means the square arrow between the average square error between X star and also the last iterate, the result, I mean the XK, the last iterate of the algorithm.
So what does it mean? Like, I mean, at the end, your problem, you want to come up with a solution and.
Yeah, come up an estimation of the solution, and so if the number of iterations is larger and larger, yeah, if the number of iterations is larger and larger, the solution will be more and more accurate.
Yeah, so which means that just convert the error doesn't change if you keep doing the middle iteration, is that right? So you're looking at the error, the difference between the current one and previous one. What is that missing?
The NIC means the error. So yeah, for each instance, we calculate the difference between our prediction and the ground truth,
Yeah,
and then
that's
we
what
take
I
the
got, but you say, yeah.
take the average.
Yeah, okay, good.
I think translating into machine learning, the V is the Y.
Huh?
Translating, okay, so translating into machine learning, the V.
The V is the Y.
Is the Y,
Yeah,
yes, it's what you observe. So it's like there is a hidden something we generated, like we have a picture of a cancer in an MRI or something, but what we get is we get some kind of observation out of that, and we try to reconstitute the input we generated on it. And if you assume that there is no regularization, then it's an ear-post problem. If you do an L2 regularization, it's the result is assume something. And at some point, some years ago, people started to all over the place that if we regularize on L1, then it's best because we don't need that many training data and other stuff. So the reason why this explodes, but then the problem is that despite the fact that with L2 regularization, Gauss had solved all these things, because of the L1, which has the kink in the absolute value, this is not solvable except through iterative methods, and then everybody is trying to find the right iterative methods for it. I guess that's the story, right? That's my
Exactly.
machine learning narrative on this one.
Okay, yeah. Okay. Okay, yeah. So because we observe that the learning algorithm works pretty well, convergence very fast. But how to understand it? Can we get some principles from the learning parameters? If we can, it helps us to understand the role of those parameters. So we find that if we assume the Lista framework to be convergent, we assume that it is convergent, and then we find that the parameters are not free. It must satisfy an asymptotic condition like this. So as long as you want your algorithm to be convergent, and it will be satisfied. And so we also validate. We also observe the learned parameters. We observe this residual, the residual of this term, and we find that yes, it goes down and down, and clearly we can see that it satisfies with our theoretical findings. It is, and this inspires us that we can just fix the coupling relationship between the two matrices. If we can fix that, we will get a reduced model like this. So in this new model, the number of parameters is reduced because because the A here is the A here is typically a fat matrix, and the number of parameters is can be reduced like two matrices to one matrix, and we find that okay, with such a parameter reduction, there's no loss of performance. We can observe the two curves, this Lista curve and Lista CP, the weight coupling term. We find that at the last iterate, they intersect. And people may ask, okay, why only report 16 steps? It's because it seems that okay, the Lista model converges pretty fast at the 15 and 16 step. Is it possible that it will be faster if you observe more? And here, we report 16 iterations because we only train for 16 iterations. The capital K here is just a 16. And yeah, so if we did some experiments, if we train and test on 20, 30, even 40, both so the Lisa and Lisa CP will always intersect at the last iteration. Yeah, so this is yeah, so
in validation, the performance did not decrease or even slightly better. But in training, I suppose since you reduce the number of parameter, the training much easier compared to the vanilla
yeah,
stuff.
the training the training time can be reduced. But because number of yeah, so finally we can, if we reduce more and more parameters, we will show it later. We can reduce the training time from several hours to several minutes. Yeah, but for this one, the Lisa CP cannot achieve like several minutes.
Lista is from Jan LeCun and Lista CP is yours?
Yeah, exactly. Yeah. Okay, so this is the first one, and also yeah. So and another direction to analyze this algorithm is, can we get some sufficient conditions of convergence? Okay, so what kind of conditions it is convergent? And yeah, we show that there exists a sequence of parameters to make the algorithm this algorithm converges in a exponential rate. It's an exponential decay convergence. And yeah, so this linear convergence is actually much faster than ISA, and even faster ISA's sublinear rate. And also, this also answers. Sublinear rate means it's it's slower than the linear convergence. Sublinear rate means that okay, for ISA, this term should be 1 over k, and for VISA it's 1 over k squared.
Now, when you say we, did you show who's the authors of this CP?
Lisa CP is ours algorithm that I showed before, by coupling the two, coupling the relationship, because we find this is also our findings. Yeah.
What role are you in this group? Who's the team that worked on this?
Yeah, I will show it. Yeah. Oh, sorry. Yeah, I'm in this paper. This is the first paper. Yeah.
And then you have like equal contribution for the first two others, right?
Oh yeah. So yeah, for all for this paper is equal. Yeah, me and Chen are equal.
What Chen doing now?
He's also he's also in Alibaba now. Yeah. Yeah. And also, this answers a question that how fast a learned algorithm can be. And yeah, to the best of my knowledge, I think this is our result is the first answer to this kind of question. Yeah. And yeah, so and also from the mathematical proof, we can even get more insights from it. So yeah, so in the theorem, we actually show that the convergence rate only depends on this quantity. It's called generalized mutual coherence. It is a extension to the standard mutual coherence. Yeah, this concept is a very fundamental concept in comparison sensing theory. And so yeah, let's look at this quantity. So it means that this quantity measures the maximal term of the off-diagonal terms of W transpose A, because WIK means the ith column of WK, and the AJ means the jth column of A. And this term is off-diagonal terms because we assume that I is not equal to J, and off-diagonal terms of W transpose A. And yeah, we also scale the W so that the W so that diagonal terms of this matrix be 1. So it means that we want the off-diagonal terms to be as small as possible and keep the diagonal terms to be close to 1. So it means that we want this matrix to be close to the identity. Yeah, so it means that actually the WK can be interpreted as a preconditioner. We want to if A is a very ill condition, we can make the whole matrix has a better condition number, and this is the this is the explanation of the roles of the role of W. Yeah, and based on this theory, we can see that okay, the optimal WK can be found by minimizing this quantity, and WK only depends on A, and A is fixed. It's not related with K. Yeah, so to numerically validate our results, the first step is to we use a uniform WK for all A. We write it as W, and it is for flexibility, we introduce another scalar here, gamma K before the W here, and it is called tied lista. We tied the WK for all K, and in this iteration, the number of parameters is further reduced because there is only a single matrix and a sequence of scalars. Yeah, and we can see that okay, yeah, so their performance looks very similar, and the new scheme tied lista looks even slightly better. And the second step is to justify. So, what's the in our theory we explain the WK as a preconditioner, but if you learn it if you learn it in practice, you still learn the W also a preconditioner or not, and we monitor the training process. So here the horizontal axis means the training progress, and we observe the coherence here. We find that okay, it reduces and reduces. So yeah, so this aligns with our explanation, and yeah, we can just regard W as a preconditioner, and since W can be explained, and we seems to have a very clear understanding now. So we just propose to we can calculate the W directly instead of training, because we know what is W here. So how to calculate it? We use an approximate of the previous. So in the previous slides, the generalized mutual coherence here should be maximum or the infinite norm, and here we use an approximation of Frobenius norm, like here, minimize this coherence and also satisfying the diagonal terms to be identity. And yeah, this is a standard convex program with linear constraint, and it can be easily solved. And after obtain that W tilde, we just plug the W tilde as into the iteration as a W here, and then learn the other parts. The other parts are just a scalar. It's much easier to learn. Yeah, and the number of parameters is even reduced. It can be the number of parameters can be even independent of the size of the problem. It only depends on the number of iterations we want. And yeah, the training takes only several minutes instead of several hours. So in our paper, we reported this within 10 minutes.
So you're saying, so you started with optimization problem, talk about the star standard one, and then the deep learning method. So and you show earlier the layers, right? That's what you're learning. So to learn those parameters, what optimization method are you using?
We use SGD with moment.
Then there's the other one here, quadratic programming.
Yeah.
So you started with original appearance problem, then you're using lots of other things, right? You're using gradient descent, gradient descent, then quadratic programming.
So for this problem, we just use Vista. It's a fast version of Vista. Yeah, and yeah. So solving this problem is much easier than training. Yeah, training takes several hours, and this one takes it can be solved with 1 or 2 seconds.
I mean, at the high level, when I look at it, so you want to solve one problem, but then which is the optimizing problem, then you need to solve two, three other problems were also optimization. So it's a
Yeah,
pretty messy.
it's a like a bi-level. Yeah, yeah.
Okay,
Yeah.
thank you.
Yeah, and this is the final result. A lista is the version. Yeah, the black curve. Yeah, and we can show that it performs good. Yeah. And also, yeah, in another paper, we also further reduce the number of parameters. So I don't want to show so many details about the formulas here, but the key information is, okay, now these parameters in the lista can be even like calculated, and now the only three parameters in these formulas are C1, C2, C3. So now the number of parameters is reduced to three, even independent of the number of iterations. And since there are only three parameters, it's okay to search the parameters by hand. It's doable by just by grid search, and we do it. And this is the red curve measures the hyperlista. Yeah, it works pretty well and very robust. We even did some experiments that there's a mismatch between training set and testing set. They follow the different distribution. The first one, yeah, the training and testing are matched, but for the other three ones, we change the distribution of testing set and it works well.
So why do you get better generalization here? Although you have.
So my understanding is that so we reduce the number of parameters, and yeah, so if the number of parameters is larger and larger, the capacity is larger, but it may hurt the generalization. Yeah.
I think the story is you have, you want to use AI, you want to benefit from AI to help you accelerate the algorithm. If you give too much freedom over there, it could overfit the problem distribution. So basically you want regularize the tree itself with some mathematical knowledge. And when you regularize the tree itself, it gives you more mathematical guidelines. So just like the solve problem itself, when you have like the sparsity over there in the solution, it have better generalization. The tree itself will also get a better generalization because you use some math knowledge to regularize the tree itself.
Yes.
There's a
Talk about
regularization of
one more.
normalization.
And do one more time. Regularize the training of the training.
That's also true. The SGD itself can be regularized too, right?
Yeah. Okay, so this finished the first part of my presentation, and let's quickly review. Okay, so for the regular Kunz work, the vanilla lista, it's a process from mathematics to machine learning. Okay, the number of parameters number of parameters is enlarged, and they obtain a black box algorithm. It works pretty well, but not that easy to be understand. And so our work is like a reverse process. We start from machine learning model to a mathematical algorithm, and we try to understand the learned model and get insights to get a smaller model, and the number of parameters is reduced, but it is a white box algorithm and it works even better. So this is the whole picture, and there are some limitations of this work looks well on these settings, but there are some limitations. The first one is it requires a fixed matrix. So if we want to use it in another matrix, in another settings, we have to train another model for that. And also, the whole methodology is highly dedicated to Lasso because the frameworks is like derived from Lasso. Yeah. So an ideal story is like we want to find a uniform methodology. When we get one data set, okay, it can be learned and to learn an algorithm and make it adaptive to the first data set. If you have another one, and it can be adaptive to another one, that will be a better case. And next, I will show that how to achieve this goal. Yeah. So now let's look at a general problem. It's we assume there's no constraint and just f here. And typically, so many iterative algorithms can be written in this abstract form. The TF here is an operator that depends on the F depends on the problem. And how to learn an algorithm, how to learn an algorithm, find some, if we can learn an algorithm, it means that we find we can this is an algorithm discovery, not just learn the promise, but learn the specific numbers in it. Yeah, so the key point is that we learn an operator instead of the specific numbers. And yeah, so yes, so this group is a deep minds group, and they find that okay, people can just use a neural network to replace the operator here, and okay, and then yeah, using the similar training method as before, we can find that okay, we can find a neural network serve as an update tool or an operator. So yeah, so once the neural network is trained, and we can find that okay, we find a new algorithm. So this is a more general settings. Yeah, it's very general as long as we can access to the gradient of app. Okay, it work. Yeah, it is doable. And so this is experiment in their papers, and LSTM is their proposed method, and they can find that okay, it works very well. It works better than these baselines. Well, if you slightly change the distribution of the, even slightly change the distribution of the testing problems, people find that okay, it may diverge. So it's not reliable, not stable. And there has been some papers, a lot of papers reporting this phenomena, and I think this so this topic is still an active topic in the literature. So we understand this issue from another perspective. So now let's recall the formula here. Okay, so neural network, this is a neural network, and as we know that neural networks are universal approximators. So given a continuous function, there is a neural network with proper parameters that is as close as possible to the given continuous operator. So therefore, when we train the algorithm, when we search over all the possible neural networks, it actually means that we are searching over all the possible continuous operators. So it's almost equal to, we can just search over a very large space, continuous operator space. Yeah, the input and output, input is this one, output is the x, is the update direction of xk. Yeah, so
can I comment here? My understanding is that they used an LSTM, and that means that is actually an inconfigured state, because they were considering the history. So what they have used there, that was they considered the neural net to be an LSTM, which means it had the history. It didn't depend on xk, it depended on xk. Something.
Oh yeah, this is a simplified writing here, and do not write the history, the hidden states. And in our analysis, we actually in our analysis it is involved. It can be involved in the historical information. Yeah. So okay, now let's okay. So what will happen if we search over all the possible continuous operators? Let's see an example. Okay, now we suppose that the training set is it involves a type of quadratic problems, just minimize a simple problem, and the testing set is slightly different. There's a shift between the optimizers of like training set and testing set, shifted by 1, and so the training means that okay, we are exploring all the continuous operators, and okay, we want to find that okay, we want to find a method that converges on the training set. Yeah, and what will happen in the training process? In the training process, first let's look at this operator. if we plug, okay, dxg equals to a scalar times g, yeah, plug it back in, and we can get a standard gradient descent. Yeah, surely it works, and on these simple problems, and it works well, and okay, it converges to the minimizer of x star. But if we see another operator like this, if it equals to 1, x, and we plug this operator back to the formula, we can find that, okay, xk plus 1 equals to xk minus xa, it equals to 0. It means that given any x0 from the first iteration, okay, the iterator will be constantly equals to 0. 0 is good because in the training set, the minimizers are 0. So okay, but the machine doesn't know that. Okay, the machine will think, okay, the second operator is better than the first one because it converges in one step. But as we know that the second one, surely it is not a good algorithm. If we slightly change the problem, it fails. Yeah. So okay. Yeah. So this is this example can somehow show why it is not that stable. Yeah. And so yeah, the learned algorithm can be very specialized to the training set, but overlook some fundamental principles it should satisfy. So we also adopt the similar ideas as before. We suppose the algorithm to be convergent, and we want to find that, okay, the operator should specify something, and then we derive a structure of that. So this is a motivation, and this is the settings. Okay, the first step, we assume that, okay, f is a differentiable convex, and the gradient is Lipschitz continuous, and in this and for the algorithm here, we use dk here. Dk it depends on k. So yeah, so I hope this can address your question, Professor Brown's question, that okay, because it can involves because dk can be regarded as a d, and it's related with some hk, and it actually involves the LSTM. Yeah, and okay, we assume that dk is continuous, and also here we assume differentiable because if we train the algorithm, we require the operator can be differentiable. Yeah, and the core assumption here is the first one is we assume that the algorithm converges to one of the minimizers of fx. Okay, so there exists x star. It's a minimizer of fx, and xk converges to x star. And also we also assume that, okay, if the xk is already x star, the next iterate will be fixed because it's already the optimal solution. And these are the core assumptions. And based on these assumptions, we find that, okay, the operator can be written as a linear rest form related with the gradient. And if we plug this operator back to the iterative scheme, and we can find that it's actually a generalized version of gradient descent. Yeah, so the difference between this one and the standard gradient descent is there are pk here and also bk here. So pk here can be viewed as a preconditioner, and the bk here is a bias term. And in our theory, we find that the bk must vanish asymptotically. Yeah, and so because the operator satisfies this structure, so it is so this inspires us that instead of learning the whole operator, we can actually, so because we want our algorithm satisfy the two basic conditions, and actually we can use the neural network to suggest the preconditioner and to suggest the pk and bk instead of the update direction dk. Yeah, so hopefully it will be more reliable. And this is the easiest case. We assume the f is differentiable and convex, and also we extend it to the non-smooth case and use a subgradient. And in this case, we have to use an implicit form to make the convergence more stable. Implicit form here means on the right-hand side of the equation, it is xk plus 1. It's an implicit formula instead of explicit formula. And so this is an implicit formula, and also this is an inclusion because subreading may involve multiple elements. So yeah, so how to solve this? So yeah, if it converts well, but how to get xk plus 1 from xk? And we find that if we do the similar analysis, we can find that okay, it can also have a similar result as before. And fortunately, this kind of result can be written as an explicit form. Like this, we use the concept of proximal operator. Okay, this is a standard operator used in optimization. And yeah, this is generalized form of classical optimization algorithm called proximal point algorithm. If we reduce the pk as a scaled version of identity and bk as 0, it reduces to a standard proximal point algorithm. Yeah. So this is a non-smooth case, and we also get some analysis on a mixed case. If there is a smooth term, a differentiable term plus a non-smooth term, and yeah, we analyze a mixed update rule and also get a similar result, and it can be reduced to a generalized version of proximal gradient descent. It's alternatively do a gradient descent and then do proximal on R, gradient descent on F and proximal on R. Yeah, and also we also do some analysis to make sure that because in previous analysis xk depends on xk plus 1 depends on xk, and we also introduce another yk. It may depends on longer historical information and involve information of y here, and then do some analysis. And this is the final suggested scheme. And so the highlighted parts are free parameters. They are not determined by mathematics. And the black parts in this formula are all determined. It can be calculated by mathematics. Yeah. So yeah, in practice we use we use diagonal terms to make the computation more friendly. And then use neural networks to suggest those terms, suggest those parameters. So actually, the model can be viewed as okay. We separate the whole operator into two parts. Some part can be calculated, and some parts are not determined. And it's like a heuristic, and we can get the heuristic by neural networks. Yeah, and also we do some evaluation study to compare to figure out the role of those components. So what are important and what are not important. Yeah, so yeah, so this is so because we don't have enough time, and so finally I just want to show the conclusion is that okay, we find that so by the numerical experiments, we show that okay, only P and A here are important. So P can be regarded as a preconditioner, and A here is actually a generalized version of natural scheme. Yeah, it's like so yeah, so instead of learning the whole operator, it's enough to learn a adaptive preconditioner, and also it's called accelerator in our paper. And yeah, P and A are suggested by neural networks, and we do not create any new machine learning models. So what they do? I mean, in the first paper, and we will follow the machine learning model and follow their machine learning model to do fair comparison. Yes.
Those are neural network structure, LSTM and MLP.
Yeah.
So you just use the data to feed in the neural network to get the algorithm.
Oh, yeah. Okay, yeah. So this is the result, and okay, L2OPA is the proposed method, and we can find that it converges pretty stable and fast. It gets stuck at 10 to the -7 because we in our experiment we use single precision. Everything is single precision. So yeah, the L2OPA converges very fast to the to the machine precision. Yeah, and also we did some experiments on real data. So we train the algorithm with randomly generated data, but test it directly without any change on real data, and it still works and performs very stable, like this. Yeah, so this is the second one, and also yeah, the whole yeah. Let's do some summary here. The first one is okay, a black box model. Yeah, it can work on solving optimization problems, but some parameters and components in it might be redundant. So we can use some domain knowledge to reduce the model and make it more explainable and reliable. And yeah, so I think a long-term goal of this field can be like make this field more and more principled and make it a real science. Instead of just a trial and error like this. Yeah, so let's talk about some future direction. The first one is sure, because in the previous slides, there are only very basic and fundamental settings of the optimization problems, and like the lasso and also the minmax and F. There are some other more complicated and also more practical, more useful settings that we didn't explore. Surely it can be a extension to those complicated settings. This is the first one, and also I think all the analysis are focused on the model or the algorithm, and I think the data part or the generalization part is also very important, and also I think it's still not well established in this field, and there are two directions to do. The first one is how to measure the generalization, like how to measure the generalization gap using the statistical tools, the statistical machine learning tools, and give some theoretical guidance. Okay, how many samples you have to use, and what kind of samples you have to use to get a meaningful algorithm, and also how to improve the generalization. Can we generate some data? If we have only like 5, we have 10 instances, can we generate more instances that are similar to those the given instance? And the last one is large language models. Although I don't have any papers on it, but I closely follow the advantage in this field. And yeah, I think algorithm discovery would be very interesting. And so in this kind of works, I think the paradigm is changed from training models to prompting models like this. And I called this kind of method as evolve and evaluate. Evolve means that, okay, tell the large language model, okay, I want to solve a problem, give the problem description. And I have 2 algorithms now, and give the algorithm description, and then give me a new description inspired by the given 2 algorithms. And someone shows that, okay, this kind of prompting works, and okay, the like ChatGPT can give you can return you a meaningful algorithm, and we can evaluate the new algorithm returned by large language model, and repeat this process, and it's hopefully we can find a good and new algorithm. I think this is this would be a interesting direction in the future. Yeah. So I think this kind of direction can still adopt the idea that I introduced before. Are there any necessary conditions that an algorithm should satisfy for a specific type of problem? And okay, we tell the large language model you should satisfy this kind of conditions, and I think the exploring efficiency will be improved. And okay, this is a direction. Yeah. So these are references, and thank you for
also like the algorithm discovery on some other statistical fundamental problems other than the so such as PCA, principal component
Oh,
analysis.
yeah, yeah. Sure. Okay, yeah. One question.
Yeah, should be,
Yeah, you can, you should close the.
Thank you. Okay, thank you for attending.